And we are rocking and rolling. All right, let's go. So, yesterday we talked about the particle theory of matter, and this is a handwritten note. Look at us, like the true 1960s teacher that I am. I find with each passing year, I basically, you're good to go. 4 minutes, be quick. As soon as she's back, you're good to go, okay? With each passing year, I just turned more and more into my grandfather, who was like a math teacher in like the 70s and 80s. And I just find that like with each passing year, I'm like, I used to be like Mr. Tech. I was like, oh, let's do everything on computers. And COVID happened. Now I'm like, I'd like to never see another computer again in my life. If I could get an overhead projector, like the old-fashioned one, and just write on that, I would. It's just, I've entered my Luddite years. But that's okay. So we talked about matter and particle theory, and we said definition of matter is anything that takes up space and has mass, right? And that it's made of individual, let's try that again, made of individual particles, right? Like little Lego blocks. You know them as atoms. You might know the term molecules, ions, things like that. We'll talk about all those terms, what they mean. But basically, everything that's matter, everything that's stuff, whether it's the air or the table or you, is made up of individual little particles that are all stuck together. The simplest of these we call atoms. And that basically they're stuck together in almost all cases. In this room, the only matter that isn't stuck together is light isn't matter, right? The light, the air, right? The air particles are different. They're not stuck together, which is why you can just walk through them, why you can push them out of the way. They're still there, right? Like if you push them fast enough, you can make somebody else's hair move, right? So they're there, but they're free. But all the other ones stuck together. They make hard surfaces, or maybe they make liquids, right? You got some liquid there. But we basically said that particles naturally want to stick together, right? There's a bond holding them together. And on the other side, while they're always being held together by a bond, they're also always constantly in motion. And those two things push against each other. The fact that they're stuck together.
Interruption staff at this time, any grade 11s and grade 12s that are under 17 and would like to participate in the free dental screening, you may now head down to the nurse's room.
I'm so sorry I just left my coffee on your desk, by the way. That's very inconsiderate. Sorry. If I could just leave my stuff on your desk, please feel free to yell at me and be like, hey, Orlando. You don't yell, that'd be rude, but you get the idea. Be like, hey, Orlando, could you come get your stuff, please? Anyway, yeah, so those particles are constantly being pulled together, but they're also constantly moving, which is trying to pull them apart. And if they're not moving very fast, then the pulling together wins. What do we call that state of matter? Where they're really just held together. A solid, right? In the case of something being a solid, what did you say? That's a good answer, because absolutely, it's a bond together. What makes a solid is a strong bond, right? And so as long as that bond is strong enough that even though the particles are moving, they can't move away from each other, we call that a solid. If they get moving fast enough that they can move away from each other, but they're going to get pulled back, so they can kind of stretch and flow and change shape, but not totally break away from each other, what do we call that kind of state of matter? Liquid. Great. And how do you make that happen? Well, if something's solid and you heat it up, the particles are going to move faster, and that means that you'll get a liquid. And if we move faster still, so that now they can move away from each other but get all the way away, just fully pull away and go free, we call that a gas. Good. Any questions about that? So solid, liquid, and gas. And the idea being that the faster the particles move, we call that heat. So a faster moving particle, we would say that it is hotter. And a slower moving particle, we would say that it is colder. That's the particle theory of matter. I left you with some words to define. And this is homework, so I want to explain something about homework, which is that when I give you homework, I don't tend to give a lot. All right? You'll notice I didn't give you 100 questions. I give you a little bit. But the expectation is that that's stuff you're going to do on your own and you're going to know it. Does that make sense? I sometimes will take homework up and sometimes I won't. And sometimes I'll take 1 or 2 questions up, but I won't always take it all up. Because the point is, you're high school students now, and you've got to be deciding whether you want to be academic stream or applied stream. You've got to be making these choices. Part of being a high school student is you've got to be an independent learner. And that's especially true if you want to carry on from here and take the academic strand. Does that make sense? So I'm not going to take 2 minutes and write down the definition for each of these. You should have done that in your own words, in terms that you can understand. I do want to quickly verbally take them up. And of course, I am going to check this. When am I going to check? End of the unit, right? Now, the problem is at the end of the unit, That's when you're going to be writing a test to see if you know your stuff, right? So there's two ways I'm going to test this. One is I'm going to check your notes, but the other way is when I ask you about it on the test and you don't know the answer, that's a pretty good sign that you didn't do the work. Does that make sense? So again, treating you like adults here. It also means I don't check homework the day after because I also understand you have lives and you may have had grandma's house to go to last night, or you may have, who knows, a hospital visit, or you may have been sick, or your dog may have been sick. I don't know. So I also get that it may take you 2 days to get to it. The best time to do it's the day I gave it to you, because then things aren't piling up. But there is a bit of freedom there, right? My advice is always do your homework the day of. So much easier. But you got a bit of freedom, right? Really quickly, what's it mean to melt something? Yep. You move something from a solid to being a liquid. How do you do that? What do you have to add? Not add water. You got to add heat. You're not wrong, though. There's something similar. Because sometimes we think of melting as being another thing we can do, which is called dissolving. That's not on this list. But if you add water to something that dissolves, it will actually join with the water. And we're going to talk about that today. So I like that answer, actually. But here specifically, to go from solid to liquid, we add heat. Now, I, of course, would want a full sentence answer from you. This is just kind of taking a quick note. What's freezing? Let's try that again. What's freezing? Yeah.
Change of liquid to solid at a fixed temperature.
Good. And what do we have to do here? We have to remove heat, right? We have to cool it down, right? If you want to move something down, and you're right, it happens at a fixed temperature, which means that there's like the freezing point. What's evaporation? Yeah. A liquid to a gas. And for that to happen, we have to add heat. Boiling is that happening at a fixed particular temperature all at once quickly. It can also happen slowly where just some of the particles get enough heat, right? Boiling, it happens at the heat source and it's all boiling at once. What's sublimation? That one, let me ask you, is this one you'd never heard of before? That to me is a term that a lot of people don't know. But what's sublimation mean? If I only see a couple hands, that tells me only a couple people did their homework, which means maybe we'll come back to that. And I want you to look it up. I want you to know. Yeah, we'll come back to that. What's condensation? Yeah.
It's like when like a drink, like the water of the coldness, when it starts to like get warm, the water.
You get water on the outside. Now let me ask you, where did the water come from? Did it come from inside the glass? No, where did it come from? The air, because there's always some air, there's always some water in the air, and if you get it cold enough, it turns back from a gas into a not solid. Maybe that would be different. That'd be frosting, right?
Yeah.
Like you've seen that before. But in this case, just condensation. That's when we take a gas, in this case gaseous water, and turn it into a liquid, and we do that by cooling, right? That's why we get dew, right, in the morning. Not actually in the morning, it actually happens in the evening, but you discover it when you go out in the morning, right? Because if you have nice, moist, humid air, and then overnight the air cools down, the air can no longer hold all that water, and so some of it condenses from a gas back into a liquid. Good. Yep, exactly. It's also like, if you breathe onto the mirror in your bathroom, right, and it fogs up, that's because inside your mouth, there's lots of moisture, and it's fairly hot, right, body temperature, and so the air is able to absorb a bunch of liquid into gaseous water. When you breathe it out, the room is cooler, the mirror is cooler, and so that turns into liquid water. Same with steam, right, where like you're in the shower, the air in the shower gets really hot, so it can absorb a bunch of water, and then as that leaves the shower and goes out into the bathroom, if you have a fan that's strong enough, I have 2 bathrooms, and one of my bathroom fans is like super strong, like it just gets every last bit, so the mirror never fogs up. And then the other one, you turn that fan on, and it's like noisy as all hell, but like it doesn't do a thing. I don't know if you have anything like that. And so my assumption in that case is that I probably should replace the fan. I'm going to get on that any decade now. But without the fan, it's bad, right?
Yeah.
My kitchen doesn't have a fan, and every time I cook, the fire alarm goes. Just every time I cook, the fire alarm goes off. It's so infuriating.
Goes, like, when there's nothing in the cupboard.
We call it the cooking alarm. Like it's just every.
Our fire alarm goes off.
Does anyone else have that? Like where every time they cook, the fire alarm goes off? It's so miserable. Oh, it's so miserable.
No, but my nana used to in her old
Yeah.
age. She, like, when we came to visit, and then she was cooking, and the fire alarm went off, then we'd see her, like, going down the hallway with a wooden spoon
Well, the other problem too is I think it's made me like immune to it. Like we had a fire alarm the other month, and at night, and it was just my son cooking at like 1 a.m. But I just like slept right through it, so that's not good, right?
Oh, no.
I think you hear that thing too many times, it stops freaking you out. So now I've learned that if my house catches fire, I will just sleep through it. So that's depressing. Anyway, hopefully somebody, and I'm heavy, right? So it's not like what, like my daughter who's like, she weighs like, I don't know, like probably like 98 pounds. She's a little skinny thing. She's not going to carry me out, right? My wife's a little thing. I don't think the two of them could carry me out. My son lives in Toronto now. My other son, he's 6. He's not carrying me out. What I'm saying is I'm dead. I'm done for, right? So no fires. Fire's bad. Anyway, we'll move on. Enough about my fears.
But did they wake you up?
Yeah, and then the worst thing, like, the worst thing is, like, you take the battery out of that thing to, like, shut it up, and then it's like, do you remember to put it in? That's not good. So I did get a smart fire alarm, and this one's actually, it's like the Google branded one, which at first I was like, I think I'm getting ripped off here, because it was like 4 times as expensive as a normal fire alarm. So I was like, and I'm a cheapskate. Boy, am I a cheapskate. I do not like to spend money. But what I like about it actually is during dinner time hours, if the alarm goes off, it actually starts really quietly, and I get a notification on my phone, and it's like, do you wish to silence this? And it's like, yeah, I'm cooking. Silence. But then, like, outside of daytime hours, if it goes off, or if, like, it knows that nobody's home, because, of course, Google is spying on you constantly, which is its own thing, then I have that turned off. I have the location tracking thing turned off because I feel weird about it. But anyway, point being, I probably should just turn it on because I probably should value my not catching fire more than I value Google not knowing all my information. But there's a real thing where I think, like, it's weird that your generation, like, 3, 4, 5 corporations know everything about you. And, like, you're just fine with that. Like, you click that agree thing when you install a new app, like, without even reading it, right? You don't read it. And even the ones that make you scroll through, you just scroll through and then you click it, right? I know you guys. And it's like, but it's weird. Like, just so you know, like, Google knows who you are so much to the point that, like, and I watched a whole thing. I read a whole article about this, like, in data. I'm into data science. If you log in on a different device, they are in the, like, if you don't log in. So if you don't log into Google on a different device, so if somebody, an unknown user, is in a browser searching for stuff, Google is in the process of figuring out who you are based on what you're searching for, what sites you go, like just comparing your habits to the known habits, and they will match it with your account even though you haven't signed into Google. So like if you search for a bunch of stuff on a different computer that has nothing to do with your computer from a different network that has nothing to do with your network, and you stick on that for a few hours long enough that they figure out who you are, all the stuff you search for then are going to show up on your Instagram ads. Because Meta, like who owns Facebook and Instagram, knows all that. It's going to show up in your TikTok trends, and you guys just give this information away, right? It's weird. I don't like it. I don't like it. I'm becoming like a Luddite, and I'm going offline, actually, because it freaks me out. And the other thing you think is like, you know, companies, other companies pay to advertise, right? So like Google gets money from them to advertise, but they don't pay you a cent for using you as an advertising tool, right? Because they're just constantly feeding you things that are designed for you, so you'll sit there addicted to them and swipe through, so you'll see more ads, so they make more money, right? And it's a whole thing. I think the phone, you want my personal belief, should be a banned substance. I honestly think that like it is. I do. I really do. I don't think anyone under the age of. I honestly don't think anyone should have a smartphone, but I think certainly nobody under the age of 18 should have a smartphone. I just don't think it's, I think it's deadly. I think it's dangerous. I think it's terrible for your brain development, terrible for mental health, terrible for sleep habits. And of course, sleep habits are a big part of how our brain develops, so terrible for neuronal development, like just on every level. Dangerous stuff. Don't like it. Not a fan. Moving on. We'll go to today's note. Today we want to carry on from yesterday. And yesterday we said everything's made of particles. So today we want to then look at that and say, broadly, if you look at any stuff, anything in the world around you, whether it's the air or your desk or this here, we can put it into 2 basic categories, pure substances and mixtures. It's right in the title, pure substances and mixtures. So what's something in this room that is a pure substance? Yeah. Ah, good. Does anyone know what metal this is? Aluminum. Very good. All right. So a pure substance can be defined as this. Any material or any matter composed of only one type of particle. That doesn't mean one particle. Like we said, there's more atoms in a strand of your hair than there are grains of sand on Earth, right? Like, it's a crazy thing to think about, crazy number. But at the same time, if you look at any material and you look inside of it and find that every particle is the same, then we call that a pure substance. And so, for example, a block of aluminum, right? If we looked inside of a block of aluminum, so let's say I've got my little aluminum block here, there it is, and we zoomed on in, whoa, look at us, we're zooming in with a super powerful imaginary microscope, what we would find is that every single piece of the puzzle is an aluminum molecule. And of course, it's a solid, so these are held together with bonds, right? But all the same, every single particle is an aluminum particle. I'm going to label those. And of course, what do we call the smallest possible particle? Specifically, it's an aluminum atom. Very good. And these are just the bonds between them, which is not a physical thing. All right? So the bond between two atoms there's not like a little string or a little hook or something, or a little chain or something. It's a force. It's like when you put a magnet near another magnet, there's a force between them, but there's not a physical connection, right? But all the same, it holds things together. Now, to be clear, this isn't a magnetic bond, but it's the same idea. What's another pure substance? We could use the example we always use in science, because it's just such a common thing to come up in science, water. So if I had a beaker and it's got some water inside of it like this, if I zoom in on that, what am I going to find? So we take there and we zoom in on my water. Does anyone know? I mean, you all know. This is like the one chemical formula that even little kids know. What's water made of? H2O, which means what? 2 hydrogen atoms stuck to 1 oxygen atom. So we could draw that, and I'm going to draw this as first with the oxygen. By convention, we always draw oxygen atoms as red. I'm not quite sure why. And then we usually draw hydrogen atoms as white or yellow. So I'm going to draw them. So these could be our little water molecules. They look like little Mickey Mouse ears kind of things. That's a highly scientific term. Try not to be intimidated by it. And again, there's bonds between them, right? Now, in this case, is there such thing as a water atom? No. Does anyone know what we call that kind of particle? A particle that's made up of a bunch of different atoms together? We would call this water. Very good. It's a molecule. And again, that's the bond between them. Yeah, so a molecule is still a single particle. That particle itself could be broken apart, but not physically. You can't take a knife and cut molecules apart, or you can't use a filter to break molecules apart. You'd have to break them apart using a chemical reaction. So that is a single particle, even though it's made of 3 subparticles, 3 smaller particles. And that takes some getting used to. We'll talk about it. So the different types of particles you might see, you might find individual atoms. You might find molecules. These are groups of atoms stuck together. And we're going to say bonded together chemically. You might have ions. That's a word we'll use later on. You might have something called formula units. You'll see these later on. Don't worry about them. I just want you to be aware that if you see any of these terms, we're talking about individual particles. Does that make sense? Don't worry if you don't know what they are yet. You will later, I promise. You're going to do this stuff to death. Bless you. So again, it's not enough to look and say, is it all the same atom? Because in the case of water, it's not all the same atom, but it is all the same particle. In other words, yes, there's hydrogen and oxygen, but it's not hydrogen floating around and oxygen floating around. They are specifically stuck to each other. Does that make sense? And they're stuck to each other in a very specific way. 2 hydrogens stuck to a single oxygen. Don't draw this, but just as an example, this, an oxygen with 2 hydrogens stuck to it is water. Again, don't draw this. But if we have an oxygen stuck to another oxygen, and both of those stuck to a hydrogen, so H2O2, that's a different thing. Does anyone know what that is? Again, don't draw this. I mean, you can if you want, I guess. But you don't have to draw it. I wouldn't draw it. Does anyone know? Nope. That's a different thing, though. We'll talk about that next year. If you take science, well, you have to take science in grade 10. But if you take my science in grade 10, if I haven't scared you off completely, if you don't get your timetable and go, science with Orlando, oh God, I got to go see McGlynn. So if that doesn't happen, then I'll see you there. This is called hydrogen. It really didn't want me to answer that. It is called hydrogen peroxide. Again, you don't need to know that, but just to show, these are both pure substances, right? Yeah, that's right. And it fizzes up.
It hurts.
Yeah, it does a little. It stings a little bit. And like concentrated hydrogen peroxide, normally we actually mix hydrogen peroxide with some water. If you had just this purely, it's actually very dangerous. It's very, very, very strong chemical. So we water it down. We make what's called a mixture, which we're going to talk about later. So let's think of some examples of pure substances. Obviously, we already said pure water. We could talk about gold, right? Or any gold, aluminum, silver, but only in their pure forms. When you buy a gold ring, is it pure gold?
No.
Why not? Does anyone know why not? If you're buying something that's really cheap gold, it's because gold's expensive, and so they mix it with other stuff, so they have to use less gold. But even if you buy really expensive gold that is mostly gold, they still melt a few other metals into it. And they do that because gold by itself is actually pretty... Yeah, it's pretty soft. It's pretty weak. It's easy to dent. It's easy to scratch. And if you add just a little bit of a couple other metals, you can make it much harder. And so it's better as jewelry because you don't want your jewelry bending and scratching and breaking. Yeah.
This is so why, like, in the old days, when people got a gold medal, they would bite to see if it was real.
Yeah.
Because it would bend and be soft enough.
Yeah, and like different metals themselves don't actually have any taste whatsoever, but different metals actually cause little chemical reactions with your body that smell and taste differently. So like, if you, I do some plumbing, and like the smell of like copper is very distinctive, and it's different from the smell of iron. But again, it's not actually the metal you're smelling, it's actually what the metal does to your own body that you're smelling, but it's one, yeah. Yeah, you bet. 3 minutes, be quick. Other examples of pure substances, oxygen gas, right? Right, nitrogen gas, whatever, things like that, helium gas, all of these things. Sodium chloride. Does anyone know what that is? It is salt. Very good. If you stick a sodium ion to a chlorine ion, you get what we call table salt. Now, the interesting thing about that is sodium by itself is a metal that as soon as it touches water, catches fire and then releases dangerous hydrogen gas and explodes. Chlorine by itself is a gas that as soon as it touches water turns into hydrochloric acid and burns you. But the interesting thing is you put them together and you get something totally safe that in fact we need. Isn't that interesting? That's what I love about chemistry. There's this magic element to it where it like changes things. Yeah, Genevieve.
So you said chlorine is like, it will burn as soon as you touch it in water.
Yeah.
But how do people put it in pools?
So we do that because we accept that it's a little bit damaging to our skin if we put a little bit in. If you put a lot in, it would kill you, so we don't do that. If you put a little bit in, surely you've experienced swimming in a pool that has a little bit too much chlorine in it before, and like your eyes start to hurt and your skin can get a little bit damaged. We tolerate a little bit of its irritating properties because you're big and tough, so you can handle a little bit of it, but bacteria and things like that are smaller than you, way less tough. So a little bit of chlorine will cause you a little bit of discomfort, but it will kill bacteria, it will kill viruses, and destroy possible things that could harm you. So that's the trade-off. Does that make sense? This is what we do in life, right? Like, you'll find biology is full of that, right? When you get a fever is your body intentionally heating up to try to kill something that's inside of you. Along the way, it hurts you because it's too hot for your body, but your body basically knows that it can suffer itself some damage, but kill dangerous things inside of you by heating up. So, again, same thing, a little bit of damage, not something you want to be doing regularly, but again, your body's tough, you're big, you've got lots of cells, so if you damage a few of them, you're okay. But like you'll feel it, right? Like if you drank a lot of chlorinated water, you'd start to get an irritated sore throat. Like in addition to it just being gross, right? Your stomach would get upset. You do damage to yourself. Now your stomach actually would be fine. Your stomach is full of hydrochloric acid. Your stomach's designed for that, right? And it uses that acid to do what? Break down food, right? But your throat isn't designed for that, and your mouth isn't designed for that, and your outer skin isn't, and your eyes. So a little bit of chlorine, a little bit of damage. A lot of chlorine, a lot of damage. Too much chlorine, right? No good, no bueno. Yeah, and again, in reasonable volumes, and again, that's better. You'd rather have slightly chlorinated water, which can do some damage, than water full of listeria or E. coli, because those are living things that can get inside of you and reproduce and reproduce and reproduce and make you really sick, right? So we tolerate chlorine, which is an irritant, so that we can kill listeria and E. coli and things like that, so that you don't get seriously sick swimming in water. Does that make sense? Cool. Pure substances, by definition, have one phase. And that sounds kind of complicated, but a phase is just a visible set of traits. Right? So in other words, when we talk about a pure substance having only one phase, it all looks the same. In other words, it all looks the same if there's only one phase, which makes sense because it all is the same. Does that make sense? Now, obviously, we're not talking about shape. Like, obviously, you could shape it differently or scratch it differently. But if you go look at this, if I polished it up so there was nothing contaminating it, right, because it's got markers on it and dirty things like that, this section of aluminum is going to look exactly like that section. Exactly. It doesn't matter where I take it. It's all going to look the same. It only has one visible phase because it's all the same stuff. It's a pure substance. Does that make sense? If you have a glass of water, it is only one. All the water looks the same. The water over here looks the same as the water over there. Again, it might be in a different shape, a different configuration, whatever. But basically, it all looks the same. It all has one phase. Is that? Sure. Kind of weird language, but you gotta get used to it. So, what about a mixture? What's a mixture? Yes. Yeah. It is a substance that is composed of more than one type of particle mixed together. All right, so that, and by the way, it could look a lot of different ways. But you might take some material there. Maybe you get a metal like brass, or a metal like copper, or a metal like steel. And in this case, when you zoom in and look at it, what you actually find is that there's some iron atoms floating around. And then there's also some carbon atoms floating around. Iron and carbon, which one's that? What alloy? Very good, steel. So in this case, if we take steel, those would be carbon atoms. And those, why did I just point out another carbon atom? Why? Why did I do that? Oh my goodness. And that would be an iron atom. You put the two together, you get steel. But of course, that's not the only other kind of mixture. What other kind of mixture could you do? Well, I mean, there's a million. I mean, even down to weird things, right? Like, I'm looking at Genevieve's pencil case right now, and the contents of Genevieve's pencil case, big old mixture. Highlighter, there's some Post-it notes, there's air, there's erasers, there's all that stuff, right? And it's all in there, all mixed together. But of course, even if you looked at one of those things, right? Like one of those highlighters is a plastic. Plastics itself are made up of a bunch of different kinds of different particles, but then it's a yellow dyed plastic. So there's going to be little yellow dye particles in there, right? And there's also inside of it like the wick, like the little, the part of it that is designed to carry ink, the ink itself. So it's all this mixture of things. So one type of mixture is what we call a mechanical mixture. And that is, I'm going to give you two definitions. First, the technical one. This is a mixture with more than one phase.
Yeah, that's not surprising.
All right. And then there's a less technical definition, is where we can say a mixture where you can see the different parts. Right? And those are actually the same definition, but I think the second one's a lot easier to understand, right?
Is it like wood?
Yeah, I mean, wood is a mixture of so many different things. Wood is a living, I mean, it's dead now, but it was a living thing, right? It cells. There's so much stuff going on in wood, it's crazy. But even like way simpler than that, like concrete. Anyone ever worked with concrete before? My family's Italian, so lots of cement work. Is that racist? Should I not say that? But it's true. We did a lot of cement work and a lot of tiling, right? A lot of pasta. But you mix cement, what do you put together? You put some water, you put the gravel, you put the sand, you put the big aggregate, right? The stone and all that, and then the Portland cement, you mix it all together, and you can see all those parts when you look at it. And even once it's dried, the water's gone, but everything else is still there and you can see it. We built a little secondary building. It's my wood shop and then a little apartment in my backyard. And it's a steel building, but we put it on a cement floor. And then instead of laying a floor or something, because I was worried about water getting in because it's just on a block, our floor, we just polished the cement. And if you've ever done that, if you've ever seen a polished cement floor, it looks really cool, but you can see all the different, you can see big stones and little stones and different colored stones all in there. You get this kind of really neat little pattern. Yeah, Harlow. Yeah. 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 Yeah, I built a little tiny home too. Oh, see, I love it. We'll have to talk tiny homes later. Yeah. Yeah, definitely. And again, you're thinking like really big and complicated, but absolutely. You look at a tree, you can see all the parts, right? So a mixture where you can see the different parts. And so, for example, we said cement, like salad dressing, right? You look at salad dressing, it doesn't look all the same throughout. You can see little flecks of this. Doesn't matter what kind of salad dressing, but say like a ranch dressing, it's like this white creamy bit, and then there's like little black specks. There's all this stuff, right? You can see stuff in there. You get like the oily one, right? Like whatever. Pizza. Pizza is a mechanical mixture, right? You can see the dough. You can see the cheese. You can see the sauce. You can see all the stuff. I think it helps to draw it, right? Like, so you imagine if you had a cup of water and I put a bunch of thumbtacks in it.
What? I would not drink that.
The old Cure. Orlando's patented thumbtack water.
Oh, really?
Yeah. Cure's what ails you, team. Okay. That looks more like a thumbtack, don't you think? There we go. That's more thumbtacky. Okay. If this is Mr. Orlando's patented thumbtack water.
That really doesn't say.
So if you buy Mr. Orlando's patented thumbtack water, this is clearly a mixture, right? Specifically, this is a mixture of water, which is itself a pure substance, right? And brass, right? That's what thumbtacks are made of, right? Which is a pure substance. Assuming that the thumbtacks didn't have any like plastic bits on them or anything, if they're just pure brass. So you got two pure substances and you put them together, you get a mixture. And because where you can see both parts, it is what we call a mechanical mixture. The other term you'll sometimes see for this, I wrote that really small. Like I'm looking at the space you have, and I sort of, relative to the space you have, I wrote that very, very small writing. If you find that you wrote it too small, you could always just highlight your writing and make it a little bigger, just like that. Yeah, get on that. And again, when we say it has more than one phase, again, that just, and I know this is repetition, but you know how we learn things as humans? Repetition, right? That's how we learn. So more than one phase means more than one visible element. I'm going to say component. And another term for this is, we say it is a heterogeneous mixture. So when you look at this, what can you see? You can see water, a clearly colorless liquid, that's one phase, and you can see little pieces of brass, that's solid. That's a second visible phase. In other words, you can see the two parts. Oh, what's that? Looks good to me. Sorry. I get excited. I get a little ahead of myself sometimes. And again, if you wrote that a little small, just sneak on in there. There it is. So we also call this a heterogeneous mixture, which, what does hetero as a prefix mean? We obviously most frequently hear the term hetero in probably terms of heterosexual, right? But hetero means what? Do we know? Other, not the same, right? So in terms of heterosexual, it's referring to people who are sexually attracted to people who aren't the same sex that they are, right? In this case, it means that not every part of the mixture looks the same. Does that make sense? The term for people who are sexually attracted to people of the same sex as them is not heterosexual, but true, but homosexual, right? So homo is the prefix that means the same as, though also straight. That is true. Don't disagree. So let's take a look then at the alternative. If a heterogeneous mixture or a mechanical mixture is the bit where you can see all of the parts, not unlike Mr. Orlando's patented thumbtack water, which cures what ails you, unless what ails you is a sickness, then we can look at the other alternative, which is a solution. And we can define a solution this way. We can say a solution is a mixture with only one visible phase. Now we'll be back in just a moment. Or in other words, a mixture, because we said visible phase, another way of saying that is just a mixture where we said if there's only one phase, it all looks the same. So this is a mixture where even though it's a mixture, it all looks the same. And so we've got the official definition here, and then we'll give the kind of more everyday language here. different things in it, but you can't tell by looking at it. And I will give you an example.
The struggle. He's faster than this. He's faster than any teacher in this school.
Okay, let me give you an example. One of these is pure water. I took it from my water distiller, which boils off any impurities, so you're left with water that is just water. And even as we speak, it's starting to absorb carbon dioxide from the air and things like that, because water likes to absorb stuff. But this is as close to perfectly pure water as you can get, or this one is. I'm not sure, I can't remember. Literally, I can't remember, because I forget which one I dropped away. And then one of them is water that I dumped some salt and sugar into.
That one looks like the salt and sugar.
That one's the salt and sugar one.
You can tell because one's more cloudy than the other.
You know what? One isn't more clouded than the other.
Oh.
One is just in a dirtier beaker than the other.
That's fair.
You actually come look at the liquid, you're going to find that they are both perfectly clear little liquids. Yeah, this is just a filthy beaker. I should have got a clean one, but I didn't. I was able to grab a filthy beaker because other teachers just take their dirty glassware and just leave it in my sink, as if I've got nothing better to do than clean their glassware, which, for the record, I do, like eating pizza. But anyway, right now I'm not eating pizza. I'm holding up a glass. But there's no way to, oh, golly, there's no way to know, right? Like, can we know by looking at that? I'm not going to drink it because it's in glassware that was dirty from some other teachers, so God knows what was in there. But we can't tell. And the reason we can't tell is that even though one of these is a mixture, it is a solution. And in a solution, there's only one visible phase. In other words, it all looks the same, right? So, it can help draw a picture. And here, I'll draw a comparison actually between all three. So I'm going to do the first one not as a mixture. The first one I'm going to draw as a pure substance. And the pure substance we'll draw is just pure water. And if we zoomed in on the water, what we would find is that every particle is the same. Every particle is just a water molecule. So here we are. Water molecule, water molecule, water molecule, water molecule. And then the second example we looked at was what we called a mechanical mixture, right? That's the previous one we did, right? And this obviously has more than one visible phase because, as you know, Mr. Orlando's patented thumbtack water, which cures what ails you, unless what ails you is a sickness, has two visible phases, the water part and the thumbtack part. Right? I think I'd rather drink that than those like bubble teas I see people drinking. I think you give me the choice bubble tea or thumbtack water. I'm going, well, and that's why, like, listen, that's why they have menus in restaurants. Because different people like different things. I think I'm slapping a trademark on that bad boy. You try to make that, I'm going to sue you, but good. Registered and copyright. Okay. And now we have the idea of a solution. And at first glance, you look at the solution, and it looks a lot like the pure substance. What does this look like it is? Looks like water, right? But in fact, this might not be water. This could be salt water. And when we zoomed in on that salt water, what we might find is, okay, we're going to zoom in, just like before. And we find that there's the water molecules all around. There's a water molecule. There's one. There's one. There's another one. Yeah, my cup's also rather different. That's okay. I have this dream of living in a house where like all the cups match and like all the silverware matches and all the like pots match and all the plates match. But then I live in the reality of my house where every day my kids seem to be losing a cup and then bringing a random cup. Like, I don't know if they like steal their friends' cups, or I have no idea. And like there's random cutlery in my drawer that isn't mine, but then mine is missing and nothing matches and it makes me feel crazed. Does anyone else live in a house where it seems like the cutlery is always changing, the glasses are always changing, and then like 3 breaks, so then they go buy new ones, and so now you've got a mismatched set, and it makes me so upset. I just want things to match. Right? I blame my children. And now if we look in here, we might find that actually there's little salt particles floating through it, but you can't see that from a distance. As opposed to take a minute, get that kind of run. But does that make sense? This is the difference between a pure substance, a mechanical mixture, and a solution. And most of what we do in chemistry, we tend not to work so much in chemistry with chemicals in the solid form. We often will make them into solutions. We'll dissolve them in water. Yeah, Harlow. Sorry? Yeah, 3 minutes. Get out. Be quick. Sorry? Oh, I said kiddo. Kiddo, because I'm an old man. I'm an old man. Oh, really? No, you don't have to get out. I mean, whatever. Get out of here, you. No, kiddo. It's like an endearing term. If you drew this a little bit too big like I did, what you might want to do, highlight it, get a little circle with your pen, and then just kind of slide that in. See, doesn't that fit better now? It's better. Yes, sir? Yeah, 2 minutes. Which gets, we're getting close to time. Yeah, you're fine. Just be quick. 2 minutes. Go. Run without running. Walk quickly. You ever seen like Olympic speed walking? You've all seen this? You're not allowed to run, but you're allowed to walk very quickly. Seen that? Yeah. This is what I'm saying. Okay, and again, solutions have only one phase, which means they resemble pure substances. Right? Because they look the same, because they look consistently the same. Sorry, this is really messy. I'm sorry. All that matters is if you can read it. All those people back there, forget them. Forget them, they don't matter. As long as I can read it, it's fine. Sorry, I'm getting noisy. I find that by third period I'm getting a little goofy, and I find by fourth period most days I'm pretty much useless. Does anyone else feel that way? Do you not? Oh, I do. I find by the end of the day I'm just like a big lump. There you go. Music definitely better. When for years at Eastdale they never put science or math third or fourth period. They always in grade 9 and 10 put them first or second, and I kind of like that better. I just feel like you're still fresh. I feel like afternoon, you've had lunch, I don't know. That's just me. Anyway, we said the previous were what we call heterogeneous mixtures, and so here we're going to say these are what we call homogeneous mixtures. Or homogeneous. Yeah. And again, that prefix, the beginning of the word, homo means the same. So, the name just means all looks the same. I'll call them straight mixtures, don't let me stop here. All right. Lip balm. Do you say balm or do you say bomb? Like, do you just drop the L completely? Do you say lip balm? Just say it quickly. Just go. Yeah, see, there's no L in there. See, I say balm, and I feel like people give me weird looks.
What?
Yeah.
I just say bomb.
Yeah. All right. So now, guys, the next thing to note is that we also note that you can make a solution out of metals. We talked about this earlier, We call a solution of metals alloys. I want you to write that as a sentence here. We call a solution of metals alloys. You can even write it in your own words. I want someone to come up and write it here.
Okay. Because I wasn't here for that. The one before that.
Nobody came and wrote this? I asked you to come and write it. But I got to do everything? Is that how this works? I do everything. I see how it is. That's fine, guys. Just let me. Okay, I'm on it.
Yeah, we're not getting.
What?
Let me tell you something, guys. You're never going to get paid better in your life.
Yeah.
No. I'm not paying you anything. Are you kidding? Let me tell you something. Okay. All right. Let's do this. Ready? No. Yeah. Okay. Now I'm pissed off. Let's go. Okay. What do you think it costs to educate you every year in the DSPN? Average. No, I'm serious. What do you think the average cost to educate one student per year in the DSPN is?
$20. $1,300.
Anyone know? This is publicly available information. You can go see the DSPN budget.
$2,300.
Approximately $18,650 per year. For 1 year. Yeah. That's the cost. And by the way, that's not counting all the money that's already been spent, right? Like they already own the building. We already own the benches. We already own these. This is just new costs this year, right? So you factor in the cost of all this stuff and divide it by how many students been here. You can probably tack on another 20, 30,000 to that for all the schools you've been to. But just the cost this year, just the bills they have to pay this year. Hey, look at me, I'm talking here. So that right there, pretty good cash value, I'd say. And you have a job? I doubt you're making $19,000 at it. Are you? Anyone have a job and they made more than $19,000 this year? Because if so, like, good on you. That's great. So now, but that's just a start. By the way, how many years are you in the DSPN for? Minimum. 4 years of high school. What about before that? Assuming like you stick with us.
9, 10, 11, 12.
Sure. 4 years of high school. How many years of elementary? 10. JK, SK, 1, 2, 3, 4, 5, 6, 7, 8. Right? How many years is that total? 14, assuming you don't do a 12B. Again, thank you. So, let's do a little math. $18,650 times 14 years is how much money? Roughly. No, calculator. Roughly, how much money is that? What is 18,000 pretty close to? 20. What's 14 kind of close to? 10, I guess. Right? Real roughly. So what's that? Roughly 200,000. Specifically about $261,100. So it costs about $250,000 to give you a DSPN education for one person. So that's not nothing. That's a lot of money. You know who pays for that, by the way? You know who pays for that? Who pays for that? Well, who's the government? People. Yeah. Yeah, that's right. Your neighbors. Your neighbor you hate, they're paying for you to go to school. Your neighbors you love, they're your best friend, they're paying for you to go to school. Your aunts, they're paying for you to go to school. Uncles, paying for you to go to school. Grandparents? These are the adults who can't stand you for some reason. Your arch nemesis. They're paying for you to go to school. To the tune of, by the time you're done, about $261,100. On top of that, do you know what the average difference between a high school graduate and a high school dropout is in earnings per year in Ontario right now? About $12,000 on average. Now, does that mean that everyone who drops out doesn't make good money? No, of course not. Some people drop out and start a business and do amazing for themselves. Some people graduate high school and make no money, like whatever. But on average, the average difference is about $12,000. How many years are you going to work for in your life? You're probably going to start somewhere around age 16, and you're probably going to be working to somewhere around age 60, right? Give or take. So let's call that 45 years. Is that fair? Yeah. Just to make it easy. So let's say for 45 years, what's $12,000 by 45 years of making that much less money? 12,000 is close to 10,000. 45 is close to 50. We should be talking close to $500,000, right? Give or take. $540,000, $500,000. That's the average for somebody who finishes high school who doesn't. How many years are you in high school for? 4 years. Let's divide that by 4. What do those 4 years pay you over the course of your life per year? 540,000 divided by 4, about 135,000. How many courses do you take in a year? 8, right? So you can make a strong argument that each class you take, in addition to costing you whatever a sixth of, plus what's 1/8 of 18,650? 18,650 divided by 8, about 2,331. What's 2,331.25 plus $16,875? Your school, each course you take in school this year. Oh, I screwed something up there. I missed a number.
Yes, you did.
No, I missed the 5. There we are. I was going to say 4,000 isn't enough. So every course you take this year pays you about $19,206.25. How many days is a semester? Does anyone know? 86. 86 active days. Officially 94-day stretch, but there's PA days, there's this or that, and there's culminating days. But let's call it 90. Just keep it safe. Every day you're here, it's the equivalent of getting paid just for my class about $213.40. I'll tell you 2 things. 1, I don't get paid that for this period of time. B, you're in $213.40 yet today?
No.
Because if you haven't, then don't talk to me about pay. All right? End of rant. Yeah. Excellent. See, I love that. There you go. So there we go. Anyway, point being, high school education, and it's the envy of the world. That's another thing you got to know. Like, you guys have no idea. You just take it for granted. Because for most of you, at least. Maybe there's exceptions to that here. But most of you probably grew up living here in Welland or living somewhere here in Ontario, where you just take for granted that you have to go to school. We think of it as this thing like, oh my God, I got to go to school again. Without realizing that, like, for people all over the world, if they can't afford to go to school, they just don't. They don't get an education. They don't get any of this opportunity. It's a blessing. It's a tremendous thing. Even when it sucks. Even if you're like, oh my gosh, Orlando again, and the guy just won't shut up. He just goes on and on. Even my crappy teaching, a wild bless, the envy of the world. Depending on year in, year out, but those international scores, and in math and science, we tend to be somewhere in the top 9 countries in the world for education quality. Sometimes up as high as 7 or 8, sometimes down as low as 10 or 11. And actually, they also do a thing where they treat Ontario as if it was another country, and that's pretty much exactly where we fit too. You're getting a good, high-quality, not perfect education. I'd love to see it be better, but a good, high-quality education. You're getting it for free. You should never take that for granted, because there's people in this world who suffer dearly to try to get something equivalent. You know, my grandparents supported. They built a school in Haiti. My grandfather's a businessman. And this school in Haiti supported 350 kids, 3 rooms to cover kids from grades 1 all the way up to grade 12. Fed them 2 meals a day. But they had kids who walked as much as like 2 hours there and 2 hours home every single day, like just through Haitian wilderness to get there. Like, things in our country not perfect. They should be better. But boy, you're lucky to be here. We all are. So, with that in mind, like we said, an alloy is a solution of different metals. Lead and tin gives us something called solder. Copper and tin gives us something called bronze. Iron and copper gives us something called brass. Iron and carbon gives us something called steel. So you mix different metals together, you get a new thing that is a combination of the two qualities. When you mix carbon and steel, you get something that is as hard as iron, but which has more flexibility and more durability and more rigidity like carbon. You put the 2 things together. Okay, this is your homework then. It's pretty simple, should not take you long. I want to know if something is a pure substance or a mixture, and then with that, I want you to do 1 second step. If it's a pure substance, I want to, we'll come back to that tomorrow. If it's a mixture, I want to know if it is a mechanical mixture or if it's a solution. And if you don't know what any of these things is, you can look it up. Or I guess we could also add alloy to the mix. You want to tell me if it's an alloy, which is a type of solution, but we can consider it differently. And then there's a little bit of research you can do there. Look it up. Something you can Google. Something you can, I don't know. You could ask your mom. You could ask your dad. You could ask your grandma. You could ask your grandpa. You could ask your mom's friend Gary. I don't know. You can do whatever you want. Does your mom have a friend named Gary? Gary, not a name you see so much anymore. A guy named Gary I went to school with, Gary Weens, got threw me in a garbage can in the hallway in grade 9.
What about Gary? That's not from SpongeBob.
There you go. All right, guys, have a wonderful day. Listen, I won't see you tomorrow because I am at a tournament. Whoa, hey, what's that? Look at this. This looks filthy. Tuck your chairs in. You're not, what do you think, my grade 11 mutants? You don't know how to tuck chairs in? Come on now. What do you think this is? French class? No. Yeah.
I did 18, 650 times 14. I'm not exactly sure if it's correct.
Can I take a look? There you go.
Not sure if it's correct.
That looks great. Yeah, it looks good. Perfect. Yeah.
Sorry about making the comment on you're the one getting paid. I was meaning for it to be a
Genevieve, it's love. Please, can I tell you something about me that you got to know? I go off on rants. If I'm ever actually annoyed with something, I would never go off on a rant. It was a fun moment and gave me a chance to rant about how important high school is. You're great. Don't you worry. I promise you, if I was ever actually annoyed with a student, what I would do is pull them aside and let them, you know what I mean? I would never call a student out in front of everybody if I was just being fun. You're good.
I actually offended my grade 6 teacher by making a joke that sounded good in my head. But
Listen, if you ever offend me, two things. One, because I'm a person who makes a lot of jokes that run the risk of offending people. If you ever offend me, you're pre-forgiven. And two, I'll be sure to let you know privately, not in front of everyone. You're golden. Don't you worry. Yeah. Probably, I thought we'd play volleyball. No, I was thinking, I was like, should we do basketball? And then I thought, no, you know what? We're going to stick with volleyball. I think we got a tournament tomorrow, so we should really stay the course. I haven't decided yet. Yeah, I haven't decided yet. What do you think? Like, honestly, what do you think? What do we need?
Probably some, like, I guess, blocking. And,
Yeah, I think blocking good, because I think specifically blocking and hitting are two things that we didn't get a lot of chances to do with the guys. So I think playing against the guys was awesome for like digging out and for like position play and stuff. And you guys did so well. I was so impressed. But I think, yeah, probably we want to focus on blocking, getting to the net, hitting.
Yeah, and then maybe